Hello, my name is Julian Rey. I am a PhD student at the IFT in Madrid. And today I will tell you about the work I've been doing for my PhD thesis, which is about primordial black holes in an early matter-dominated era and stochastic inflation. This talk is based on the 3 papers that you can see at the bottom, and at the end of the presentation, there's a full list of references. So let me start by saying that primordial black holes are the oldest dark matter candidates. And what makes them interesting, in my opinion, is that they do not require any physics beyond inflation. There is still a very large window of masses that remains viable for these black holes, which ranges from around 10 to the minus 16 solar masses to 10 to the minus 11. And for comparison, these are many orders of magnitude smaller than the events that LIGO has observed. And this is, when I say that this is the range of masses that remains viable, I'm assuming that the distribution of the masses is very peaked. The bound on the lower end comes from Hawking radiation, and on the higher end, it comes from microlensing experiments. Something else that makes these black holes very interesting is the fact that their astrophysical signatures, namely the fact that they produce gravitational waves and lensing, is something that could be probed within the next decade. So what we want to do in this talk is we want to determine the effects on the abundance of these black holes of these 2 things. The first is the equation of state of the universe at the time at which the black holes form, and the second is the back reaction of quantum fluctuations on the classical trajectory of the inflaton, which also affects the abundance of these black holes. And we're going to explore these aspects in the context of 2 different inflationary models, one of which is numerical and one of which is analytical. So primordial black holes are black holes that are formed in the early universe by mechanisms different to the usual stellar collapse. If we want these primordial black holes to form, what we need is to have large density fluctuations, which we are going to assume are produced during inflation. Now, one can show that the fraction of dark matter in the form of black holes, which is denoted by this FBBH, is actually proportional to this function beta, which changes depending on whether the black holes are produced during a matter-dominated era or during a radiation-dominated era. Now, in what follows, we're going to assume that directly after inflation comes a period of reheating in which the universe is matter-dominated. Reheating is not the only way in which you can get an early matter-dominated era, but and it's not necessary, in fact, for the arguments that we will make. So yeah, we assume that directly after inflation comes an early matter-dominated era and then a radiation era. So depending on whether the black holes form during the early matter-dominated era or during the radiation era, their abundance is going to be different, and this difference is quantified by this function beta. If the black holes form during radiation domination, then the expression for beta is the first of the 2 that are shown here, and this is obtained by assuming that by using the pressure vector formalism, in which you assume that the density fluctuation induces collapse as long as it's above a certain threshold value, delta C. On the other hand, the derivation of this probability of formation for the black holes in the case of matter domination is done a bit differently, and you have to take into account the non-sphericity of the collapsing cloud and the angular momentum. And what you find is this expression shown at the bottom. Now, the main difference between, one of the main differences between these 2 expressions is the fact that these, in the case of matter domination, the function is a lot less sensitive to small changes in the power spectrum. And this is what is plotted on the left-hand side. So here we're showing the abundance of the black holes as a function of the change in the abundance when I change the parameters delta T and delta P, which are delta T is the T is the transition temperature between the early matter-dominated era and the radiation era, and P is simply the power spectrum of the fluctuations, which is as most of you probably know, it's a quantity that encodes how fluctuations are distributed across different scales. So if I vary these 2 parameters by multiplying them by some factor delta T and delta P, what is depicted here in this figure is an order of magnitude change in the function in the abundance of the black holes. So you can see that if we forget about the vertical axis, the most important one is the horizontal one. If we fix the variation of the temperature, say for instance that we don't vary it, so we are here at delta T equal to 0, then what we find is that by changing the power spectrum by a very small amount, right? So by varying this delta P by a very small amount, I already reached the order of magnitude change in the case of radiation domination, which is the purple curve. But if I want to reach the same order of magnitude change in the case of matter domination, then I have to vary the power spectrum by a lot more. So in other words, because the purple region is a lot smaller than the blue region, this means that the abundance of the black holes is a lot less sensitive to small changes in the power spectrum in the case of matter domination. So the power spectrum is a quantity that can be computed. As long as when you have a model of inflation, this can immediately be computed. And this is something that is already measured. Now, since it is already measured, we might wonder whether it's the value that is measured is actually enough to produce primordial black holes. And it turns out that it's not, but that's okay, because as I said at the beginning, the masses for the black holes that are unconstrained, as long as you assume that the distribution is very peaked, so it's basically monochromatic, the masses that are unconstrained are very small. And you can actually show that the masses of the primordial black holes are inversely proportional to the scale of the fluctuation that is inducing the collapse. So it's inversely proportional to K. So if you want to have very small masses, then you want K to be very large, which means that you want the collapse to occur at very small scales. And the power spectrum is actually measured by Planck at very large scales. So it's okay if we need to, so the fact that we need a power spectrum that is a lot bigger than what is measured is okay, because this is the power spectrum at completely different scales. How do we get an enhancement of a power spectrum to be able to produce these black holes? In the slow roll approximation, one can show that the power spectrum, this is a very crude approximation, but it's enough to understand the intuitive idea of what happens. One can show that the power spectrum is inversely proportional to the speed of the inflaton. And then what we need if we want to have a very large enhancement of a power spectrum is to have a feature, some kind of feature in the potential that slows down the inflaton as it goes through the feature, such as an inflection point or a small hill, in such a way that at that point the power spectrum becomes very large. And the kind of potential that we're considering is shown here on the figure of the left. You see that at first we have a more or less flat potential at large scales, and this is where we feed the CMB data. And then as the inflaton rolls down, eventually it reaches this point labeled with the PBH sign, and this is where the inflection point lies. And this is where once the inflaton reaches this inflection point, it's going to slow down, and the power spectrum is going to grow, producing black holes. And then at the end, you have the reheating phase at very small scales. And the power spectrum associated to this kind of potential is shown on the right-hand side. And you see that what we get is at very small k, we have the value that is measured at the CMB of about 10 to the minus 9. And then at larger k, we have this peak because of the feature in the potential. And this is where the PBH are produced. Now, collapse during matter domination has two very big advantages. One I have already mentioned in the previous slide. It's the fact that the abundance is a lot less sensitive to small changes in the power spectrum. And the second is the fact that the power spectrum required to get a significant amount of primordial black holes, in other words, to be able to explain all of dark matter in the form of primordial black holes, is much smaller in matter domination than it is in radiation domination. It's by about 2 orders of magnitude. So you need a power spectrum of order 10 to the minus 2 in the case of radiation domination if you want to produce enough black holes to explain all of dark matter. But in the case of matter domination, it only needs to be about 10 to the minus 4. So it's this is an advantage because you don't need the fluctuations to be as large if the collapse occurs during matter domination. So what is the simplest model that we can consider that does this? Well, what we can do is we can consider a scalar field coupled to gravity in the standard way via this term psi phi squared r. And what we can do is to get rid of this term, we can redefine the fields, meaning the field phi and the metric. And once we have redefined the fields in such a way that the new kinetic term is canonically normalized, and what we obtain is the second action that is shown here. And we can see that the net effect of this whole procedure is simply that now you're going to have a potential that is divided by this factor omega to the fourth. But omega is defined here on the second line, and you can see that omega is proportional to phi. So really what you have is a potential that is divided by a quartic polynomial. But the simplest potential that we could have chosen in the first place was also a polynomial. So what this means is that for this action that is shown here at the top, after playing around with the fields a little bit, you find that this is equivalent to having a potential that is the quotient of two polynomials. And this is going to give us exactly what we want, which is an inflection point, as long as the parameters satisfy a certain relationship. So the main issue that we find when we try this model is in adjusting the spectral index. Now, the spectral index is the tilt of the power spectrum at very large scales. And what we find is that the predicted tilt is of about 0.95, but the one that is measured by Planck is of about 0.96. So there's a bit of a tension there. And then what we can do to solve this is that there are two different solutions which are both well motivated. The first one is that we can simply extend lambda CDM, because if we add things that have to be there, so sort of such as the neutrino masses or an effective, or we allow the spectral index to run, then what we find is that the spectral index becomes a little bit smaller, of order 0.95, which is in agreement with what we find. The other solution, if you don't want to extend lambda CDM, is simply to add higher dimensional operators to the potential, which are expected anyway. And then if you add some higher powers of phi to the potential, still a polynomial, but now it's not quartic, but with higher powers, what you're going to get is that the effect of these terms is going to be to change the potential at large field values, but it's going to leave it unchanged at low field values. So what's going to happen is that now you're going to have extra parameters, which are going to allow you to fit the CMB data better. But at the same time, you're going to leave the predictions for the primordial black holes unchanged, because these terms do not really affect the potential at low field values. So these two solutions are depicted here in the figure of the left. What is shown here is this function f, which is the abundance of the black holes, the amount of dark matter that is in the form of black holes. So it's a number between 0 and 1. And this is shown as a function of the mass of the black holes. And we can see that, here we can see the two solutions, the green one and the blue one. The green one corresponds to the first of the two solutions, in which you have a fourth order polynomial only, but you allow lambda CDM, you allow extensions of lambda CDM. And the second one is with higher dimensional operators. And we can see that with either of them, we can explain all of dark matter in the form of black holes. Something else that is very interesting about this mechanism is the fact that these large density fluctuations in the scalar density spectrum induce a peak in the tensor spectrum. So you get a peak in the primordial spectrum of gravitational waves that falls precisely around the Lisa and the SIGO window. So if this mechanism is correct and the primordial black holes are the dark matter, then we should be able to see the associated signal in Lisa and the SIGO in the next few years. The last thing I wanted to talk to you about is the stochastic inflation formalism. So in stochastic inflation, what happens is that quantum fluctuations back react on the classical trajectory of the inflaton, and they modify the background evolution. One way to see this in the slow roll approximation, which is, again, it's not really true because we have to violate slow roll to be able to produce the black holes, but it's enough to understand intuitively what's happening. What you get is so what you have to do in the stochastic inflation formalism is you have to take the field and you have to split it into a coarse-grained part and the quantum fluctuations by introducing some cutoff sigma in the wave number of the Fourier modes. So once you split the field into a coarse-grained part and a perturbation, you plug that back into the equation of motion. And what you get is the first equation that is shown on here in the gray box. And you see that this is the usual equation of motion for the inflaton, but now you have an additional term that is multiplied by this function xi, which is a stochastic noise term. Now, and again, this equation is only valid in the slow roll approximation. Now, since you have this stochastic noise term, what's going to happen is that at every time step, this stochastic noise is going to give a kick to the inflaton, so that at every time step you're changing the trajectory of a coarse-grained part of the field by a little bit, and these little changes add up over time. So if you want to compare whether this new term is important or not, what you can do, because this psi is just a stochastic noise, is something between 0 and 1, what you can do is simply divide both coefficients, right, to see if the amplitude of the second one is important. And what you find is that the stochastic noise is completely irrelevant as long as the power spectrum is much smaller than 1, which is what happens in standard inflation. In fact, it's what is measured by Planck, right? The Planck measures the power spectrum to be order 10 to the minus 9. So it's so indeed the stochastic noise is not important in that case. But then we worry that it might be important in our case because now we want a power spectrum that is quite large to be able to produce the black holes. So the what you do in order to do the full calculation, what you do is instead of taking the slow roll approximation, you simply split you split the field into a coarse-grained part and a perturbation. And using the Hamiltonian formalism, you have that the field and its conjugate momentum satisfy these two Langevin equations shown here, and each one has a different stochastic noise, which we assume to be Gaussian. Now, these noise terms are actually classical stochastic variables because their commutator vanishes on small scales, which is what we're interested in. So you can forget about, after you have done this procedure, you can essentially forget about quantum mechanics and simply consider these as classical stochastic differential equations. So what we're going to do now is we're going to solve these differential equations with an analytical approach. And the way we do this is by considering a 3-region model. Now, the enhancement of the power spectrum in any of these models that we're discussing, where the potential has some sort of feature like an inflection point or something like this, any of these models, the enhancement of power spectrum in any of these models can be understood by considering a 3-region model. Now, what I'm plotting here is on the left is the second slow roll parameter eta, which is it essentially controls the second derivative, the acceleration of the inflaton. So what usually happens in this model is that eta is very small on the first phase because the field is in slow roll, and then eta grows to a very large positive value, and this is what leads to the enhancement of the power spectrum. And then at the end, eta relaxes back to a negative value and inflation ends. So what we do, the behavior of eta in a standard in the standard case, right, for a numerical model of this this type of potential is shown here in the blue curve, and our analytical model is basically the black curve. So what we do is we take the eta and we fit it with 3 Heaviside step functions. And despite the fact that this is a very crude model, a very crude approximation, it actually reproduces the features of the power spectrum quite well, including the peak and the dip. So what is shown here on the right side is the fact that, well, what we find with this, the advantage of this model is the fact that now we can obtain analytical expressions for the noise correlators, and we can explicitly compute the power spectrum analytically. And what we find is that as long as you choose the cutoff correctly, the cutoff between the coarse-grained part and the perturbation, the power spectrum is exactly the same as it would be in the classical calculation. So this formalism of stochastic inflation has no effect on the power spectrum, at least at leading order. And what I mean when I say that the cutoff has to be chosen correctly, simply that you have to choose the cutoff in such a way that you give the quantum fluctuations enough time to classicalize after they leave the horizon. As long as you choose the cutoff correctly, the point here is that the power spectrum is the same in both formalisms, at least at leading order. So in conclusion, first off is the fact that the simplest potential that can produce primordial black holes is still viable, meaning the polynomial that I showed you earlier, provided that we either extend lambda CDM or we add higher dimensional operators to the potential, and both of these are well-motivated extensions or solutions. And the second is that if dark matter is in the form of primordial black holes, then the corresponding gravitational wave signal should be observable by LISA and the SIGO if they form during, at least if they form during radiation domination. The next thing is that we have shown that at least at leading order, the stochastic inflation formalism does not have an effect on the power spectrum, even if there is an ultra slow roll phase present. Although this does not mean that the formalism has absolutely no effect on the abundance of the black holes. If you do the calculation at higher orders, you might find that including, for instance, the 3-point functions and so on, you might find that there is actually an effect. And there is some work being done in this direction. But at least at leading order, considering only the power spectrum, we find that it's the same. The next thing is that, the final one, is that the primordial black hole formation and early matter-dominated era has a few advantages compared to the standard case that is usually considered, in which they form during the radiation era. And these two advantages are, first, the fact that a smaller enhancement of the power spectrum is required to explain all of dark matter in the form of black holes. And the second is that the parameters of the potential are a lot less tuned. And that is everything that I wanted to tell you. So thank you very much for listening, and I welcome any questions that you have. Thank you.